I'm Mrs. Hannah Angelin. In this video, we are going to learn about the deflection of determinate beams and rigid plane frames by energy methods. When an external load acts on a structure, the structure undergoes some deformation and hence work is said to be done. This internal work is stored as energy in the structure and it helps the structure to regain to its original shape and size after the load is being removed. This internal work, which is stored as energy, is due to the straining of the material, and this energy is called as strain energy. Here we can see a stress-strain curve. U denotes strain energy and UC denotes complementary energy. Area below the stress-strain curve of any material gives strain energy and area above the stress-strain curve gives complementary energy. Strain energy and complementary energy will always exist in a structure when it undergoes straining. Let us see some basic relations. Let us take a structural system which carries n number of loads. An element is considered inside the structure. Let us take the area of the element as delta A, a small element. Length of this element is taken as delta x, and the load which is acted on both the sides of this element, let us take it as P. Strain energy stored in the element is given as SE in short, denoted by U. We write integral 0 to E P1 delta E dV. I'll tell you how I've written this. So here a curve is drawn between stress and strain. So as stress increased, strain also increased. And the curve is being plotted here. It is a nonlinear curve. And I'm going to consider a small element of area dA. So I can find out what is the value of stress, what is the value of strain. Here it is shown in shaded lines. Let me take it as delta P and delta E. The stress in the small element, strain in the small element of thickness, delta X. So here the limits are from 0 to E. So area under the stress strain curves gives strain energy. So the limits of integration will be from 0 to E. Strain energy in the small element has to be determined. It is given as integral 0 to E stress in the small element into strain in the element into the volumetric strain. So here let me take P, small p as a stress. P1 denotes for one element. Delta E is a strain in the small element. So here I can write delta V as delta A into delta X. What is delta A? Delta A is the area. Delta X is the length. So delta V can be replaced as delta A into delta X. I can write here as area under stress strain curve into delta V. Why I wrote here area under stress strain curve? To find the strain energy, I should know the area under stress strain curve into this delta V. This gives the strain energy of the total element. When I do the integration of this one small element, it gives me the strain energy for the total element. So area under stress strain curve into delta V will give me the value of strain energy for the total element. If stress strain curve is linear, then I directly find it as a triangle. So half into base into height. So I write here strain energy as half into base into height as the area of this linear triangle. So strain energy stored in the structure, if it is nonlinear, I can give it as U equal to integral half P into E into dV. Work done is given as force into displacement. So stress into area is force and displacement is given as strain times delta X. This strain energy which is stored in the system is taken as internal work done, that is due to the straining of the material. If the material is still within elastic limit, work done by the external load is taken as the summation of 1 by 2 P delta. Capital P denotes load Delta denotes deflection. So in load deflection curve, if I'm going to plot a load deflection curve like I did for stress strain curve, if the line is a linear line or if the load deflection is a linear curve, to find for any element and to find for the whole structure, I find out as summation of half into base into height. So it is like a triangle below this load deflection curve, half into base into height. So I told you, if it is non-linear, we take the area of this portion, take up area of this portion. So area under stress strain curve into delta V. If it is linear within elastic limits, external work done is given as summation of 1 by 2 P into delta. Summation has to be done if n number of loads are acting on the structure. We can write work done in a structure as external work done equal to internal work done. External work done is got from load deflection. We can externally see what is the deflection due to the load. So I write here for external work done summation of half P delta. And internal work done will be the strain energy due to bending. So external work done should be equated to internal work done. So now we'll find what is the strain energy due to bending and equate that with external work done to find what is the deflection. So here by the strain energy or energy methods, our main aim is to find deflection and rotation for beams and rigid plane frames. Let us see the strain energy due to bending. It's a beam element. Let us consider a small element of area delta A. It is acted upon by bending stress F on both the sides. Length is taken as L. This is the longitudinal section. I can locate this element at a distance of y from the neutral axis. This beam is said to be under pure moment. So by the theory of pure bending, we can write it as M by I equal to stress by y equal to E by R. Or I can write stress is equal to a relation with M by I and F by y. I just take y to the other side. I write M by I into y equal to F. So strain is given as, small e is taken as strain. Strain is given as stress by Young's modulus. Since this relation is equal to stress, I divide this relation with this E to have the value of strain. Strain energy in the element is given as half into stress into strain into dV. You have seen this already. So if it is a linear elastic structure, we take half into stress into strain. That is the area under the stress strain curve into dV. Or I can write half into, instead of F, I can write it as M by I into Y into, for E, I can write it as M by EI into Y into this dV. I can finally write a relation for the element as half M squared Y squared E I squared into dV. This is for one element. So if I need to consider for the beam, I should integrate the elemental values between the limits such that I have volumetric limits. I have dV. So my integration will be a volumetric integration. So strain energy in the beam is given as integral V of this term. And I can divide this integral of V, volumetric integral, as length integral into area integral. So in length integral, I take all the constant terms M squared 2 EI squared and take the variant y squared inside the area integral. Integral 0 to a y squared dA into dx. So I have written dA into dx because dV is nothing but dA into dx. Here I group this as I, second moment of area. Integral 0 to a y squared dA is taken as I. So I can get I cancelled, and finally I can write a strain energy for the beam as integral 0 to L m squared dx by 2EI. I can take this strain energy value to determine the real work done by the loads. This is given by law of conservation of energy. I can equate this strain energy which I have determined here, that is the real work done by the loads internally, that is due to bending, with what we have done already, external work done, such that I can relate both to find the value of delta. This is what is given in strain energy method. Now we shall see the methods of finding deflection of determinate beams and frames. First method, strain energy or real work method. Second, virtual work or dummy load or unit load method. Third, Castigliano's method. And fourth, Maxwell's reciprocal theorem. Let us see one by one. So now we have determined a relation, that is the work done in the structure. So this comes under strain energy method. Strain energy stored in the system is equal to the strain energy due to bending. Strain energy stored in the system can be written as the external work done caused due to the loads acting on the structure. Strain energy due to bending is given as the internal work done. Equating both, we write relations half P delta is equal to integral 0 to L m squared by 2 EI dx. So this is what is given as the first method, strain energy method. It is a real work method. It is the work done by actual loads. Let us see few worked out examples based on this method. First problem. Using strain energy method, determine the vertical deflection at the mid-span of a simply supported beam of span 6 meters carrying a single concentrated load of 50 kN at the mid-span. Take EI as constant. A solution is given here. A simply supported beam with a central point load. The values are given in the problem. We need to determine what is the deflection, vertical deflection at the mid-span. Let us take as point C. Strain energy. U is given as integral 0 to L m squared dx by 2 EI. This is the strain energy due to bending. This has to be determined and equated with the external work done, that is half P delta. So we can find what is the value of delta. Sections has to be considered based upon the loading pattern, and this tabulation is filled up. Let me explain to you. Since there is a load here and deflection has to be determined under the load, this beam AB is divided into two segments or two portions. One is from A to C, that is the loaded point, and the next one is from C to B. Sections are taken in both the portions at a distance of x from both the ends. So let's see what is written in the tabulation. So segment AC, origin is taken from A. Limits are the length of each segment or each portion. Length of AC is 0 to 3. That will be the limits of the segment AC. Mx is the moment expression about the section considered. When I am going to take VA, this beam will be pushed down. This causes positive bending moment or sagging moment. So I put here plus VA into distance x. EI is a constant, so I put here EI. If there is a variation, I will make a mention here. See for the next segment, BC. So here in BC, a section is being taken. So a section is taken at a distance of x from B. If moment is considered about the section, VB into distance has to be considered. So VB into the distance causes the moment which pushes the beam downward or sag down. So this is a positive bending moment. So the moment is plus VB into x. So with these values, we are going to find what is the internal work done in the structure. So the relation is given as integral 0 to L m squared dx by 2 EI. Here there are two segments. So integration has to be done separately for two segments and added up to get the net value. Integral m squared dx by 2 EI of AC plus integral m squared dx by 2 EI of BC is calculated by substituting the corresponding values of m, corresponding values of ei and the limits. After integration, the result is given here. So now we are going to calculate what is the deflection at the midspan. External work done can be equated with internal work done. That is what we have seen in strain energy method. Half P delta is equal to the internal work done or the strain energy due to bending. Here I can find the value of delta Vc by substituting the value of load given in the problem. The load here is 50 kilonewton. So substituting, I get the value of delta Vc. So here what we have done, we have calculated what is the strain energy, that is internal work done, equated that with external work done to determine the value of deflection. We'll go to another problem. The details are given here. A stepped beam, a variation of EI is shown. Sections are taken in both the segment. We need to find the value of delta VB, vertical deflection at B. Here, this portion limits are from 0 to 4. The span is 4 meter. This portion limits are from 0 to 3. The segment length is 3 meter. We can find what is the value of VA and VB. It is like a simply supported beam with an eccentric loading, WB by L and WA by L. With these values, we are going to fill in a tabulation to do the integration to find the strain energy internally and equate that with the external work done to find the deflection. So let us see what is written in the tabulation. So this beam is divided into two segments AB and CB based upon the point where the load is or the point where deflection has to be determined. Origin for the section AB is taken as A. Origin for the section CB is taken as C. Limits are the length of each segment. Mx is the moment about the sections considered. About the section XX in span AB, VA into X causes a moment such that the beam is pushed down. It will be a clockwise moment which pushes the beam down. Check. Clockwise moment which pushes the beam down. So I write here plus VA into X. I can substitute the value of VA. Same way for CB, the limits are from 0 to 3. Check the moment. VB into X will cause the moment pushing the beam down. So I write here plus VB into X. EI values, there are variations. So I write EI as 3 EI for AB and EI for CB. Next I determine what is the strain energy. It is integral 0 to L m squared dx by 2 EI. It is divided as the integral value for the segment AB plus integral value for the segment BC. Values are substituted. Integration is done between the limits and finally we get the value of strain energy due to bending or the internal work done. Now we need to determine the external work done to find the deflection. So half P delta is equal to the strain energy due to bending. P is the load acting at the point where deflection has to be determined. So value of P is 50 kilonewton. So finally I can find what is delta VB. Next problem. Let us see a cantilever frame. One end fixed, the other end is free. A load 10 kilonewton is acting at the free end. Variation of I is shown. The lengths are given. Given values are E and I. We need to find the value of delta VC or the vertical deflection at the free end. We need to draw free body diagram for this frame. Only then it will be easy for you to understand and fill in the tabulation. So I have divided this frame as a column and a beam. I have shown the load existing here, that is 10 kilonewton. The span of this is 4 meter. Span of this is 3 meter. So here I have shown with colored pens. Just follow me. So a 10 kilonewton load is acting at C. The other end of the beam has a reaction of 10 kilonewton going in the upward direction. These two form a single joint. So at this point, if 10 kilonewton is the reactive force acting in the upward direction, here at the same point in this column, to equalize this reaction, there will be a 10 kilonewton acting in the downward direction. So the reactions will be equal and opposite such that the joint will be in equilibrium. Finally, in this column, the reaction will be in the opposite direction to have this in equilibrium. So one load has a reaction in the other direction. One joint has reactions in the other direction for equilibrium. One column has reactions in the other direction to have it in equilibrium. Next, this 10 kilonewton is at a distance of 3 meter from B. So this will cause a moment about B in this direction, that is clockwise direction about B. So at B, it should resist the moment. So check the direction. It is opposite in nature to that of the moment caused due to 10 kilonewton. So 10 into 3 is 30, causing a moment in the clockwise direction. Resistance will be in the other end. Note the word end. End of the beam. So it will have 30 kilonewton acting in the opposite direction. For the joint to be in equilibrium, it should have an equal and opposite moment of same magnitude. Check the directions. For the column to be in equilibrium, it should have equal and opposite moments of same magnitude. So finally, from this end till the other end, we have drawn the free body diagram for each beam and column and the resisting forces at each joint. With the help of this free body diagram, we are going to write this tabulation. I have taken this as one section. I have taken this as the other section. Our aim is to find the vertical deflection at C. For portion CB and portion BA, the details are written and integration is carried out. The limits for section BC is 0 to 3. The length of BC is 3 meter. The length of BA is 4 meter. So the limits are 0 to 4. Mx is the expression written for bending moment about the sections considered. So in section BC, a section is taken at a distance of x from C. When I am going to take a section x from C, this 10 kilonewton will cause a moment in this direction towards the section such that the beam is pushed up. This causes a hogging moment or negative bending moment. So I write minus 10 into x. When I go to the next column, I don't consider all these because the reaction, the resistance is transferred to this column. So whatever is there in this column I consider for writing my moment expression. When I take section at a distance of x from B, this 10 kilonewton is acting axially. That doesn't cause any moment. This 30 kilonewton meter, it is acting in the clockwise direction. This pushes the column outside. That is taken as a negative bending moment or hogging bending moment. So it is written as minus 30. EI values are made a note here that is given in the problem. If free body diagram is drawn, then the moments about the sections considered can be easily written. Now with these values, we just do the integration to find strain energy due to bending. Strain energy is given as integral 0 to L m squared dx by 2EI. So integration for CB section plus integration for BA section has to be done and summed up. So you should take care that m squared has to be written. The whole terms has to be squared. Finally, we get an expression for strain energy. This has to be equated with the external work done with half P delta taken from load deflection curve. So here the value of P is given as 10 kilonewton at the free end of the frame. So finally substituting the value of P, I get the value of delta VC. Since E and I values are given, I can get the numerical output for this problem. Now let us see another problem. a simply supported frame. There is a load at the roller end. The values are given in the problem. We need to find what is the horizontal deflection at this roller end. Delta HD. Since this is a frame, it will be easier for us to write the moment expressions for integration if free body diagram is drawn. There is a load P acting at the support. That is a horizontal load. Since it is a horizontal load acting at the support, this doesn't give rise to any vertical reactions at the support. If this load is acting at some distance above from the support, then that load will cause reactions. Since the load is acting at the support, this load doesn't give rise to any vertical reactions, but this will give rise to a horizontal reaction. Let us see from the free body diagram. Here two columns with a beam. Let me start from the right end and proceed towards the left end. There is a load acting at point D. The value is 7 kN. This 7 kN load is resisted at the other end of the column with an equal and opposite direction reaction. At this joint, both are the same point, joint C. For the joint to be in equilibrium, it should have an equal and opposite force at point C. So here it is minus x direction force. So opposite will be plus x direction force. For the beam to be in equilibrium, the other end of the beam should have an equal and opposite force. For the joint to be in equilibrium, it should have an equal and opposite force. For the column to be in equilibrium, it should have an equal and opposite force. So by now we can find out the horizontal reaction at A will be opposite in nature to that of the 7 kN load at P. That is got from this free body diagram. Next, this load is at some distance from the other end. The distance is 5 meter. So 7 into 5 is 35 kilonewton meter acting in this direction. Let's check the direction, in anti-clockwise direction. So resistance will be in clockwise direction. So this is shown here. For this joint to be in equilibrium, there will be an equal and opposite direction moment taking place such that this is in the clockwise direction. At this joint, it is in the anti-clockwise direction. For the beam to be in equilibrium, it should carry an equal and opposite moment at the ends. Check the direction and magnitude. For the joint to be in equilibrium, it should have equal and opposite moment. It will not be transferred to the other end because it is simply supported. Moments will be released. Now we shall fill in this tabulation from this free body diagram. In the portion DC, a section is considered at a distance of x from D. D is taken as the origin. To write moment expression about the section, I have a load that is P. So P into x will be the moment acting towards the section. When bending takes place, the column is pushed inside. That is taken as a positive bending moment. So I write here plus 7 into x, or P into x is substituted as 7 into x. The length of this column is 5 meter. So the limits are given as 0 to 5. Next, for CB. For CB, for this beam, a section is taken at a distance of x from C. Here if I am going to take a section from C, the loads and reactions from C up to this section has to be considered. So here at C there is an axial reaction that doesn't give rise to any moment about the section. There is already a moment of 35 kilonewton meter acting in the anti-clockwise direction. This causes a moment which pushes the beam down if it goes towards a section. It is taken as sagging bending moment or positive bending moment. So I write here plus 35. Next, for this column, if I am going to take a section from B at a distance of x, at this point I have a reaction of 7 kilonewton. When I want to take bending moment, this will cause clockwise direction moment pushing the column outward towards the section. So I write minus 7 into x. There is a moment of 35 kilonewton meter which pushes the column inward when it is towards the section. So plus 35 is mentioned here and minus 7x is given. Strain energy is determined based upon the relation integral 0 to L m squared dx by 2EI. So integral value for DC, CB and BA, the three sections which you have considered, has to be summed up to get the net strain energy or the internal work done in the whole system. I can write external work done and equate that with internal work done to find the deflection at the roller end. So external work done is given as half P delta. Internal work done is the strain energy. Equating both, I get the value of deflection. Since EI, value of load, is given, I just substitute to get the value of horizontal deflection. This is a semicircular arch hinged at one end and on rollers at the other end. A load is acting at joint B in the horizontal direction. R is the radius of the semicircular arch. Since the load is acting at the support, this doesn't give rise to any vertical reaction, but this gives rise to a horizontal reaction. For a small element of length dx on the arch, to write in terms of theta, I have considered a small segment. Angle is d theta. Length in the linear direction is dx. Length dx is equal to r times d theta. Wherever I write the expression for dx, I substitute as r d theta. The limits of integration will be from 0 to 180 degree, that is the angle included in this arch. Or I write 2 times of 0 to 90 degrees. For mx, I have substituted pr sin theta. For dx, I have substituted r d theta. Sin squared theta is written as 1 minus cos 2 theta by 2. After integrating, the expression is obtained here. Now, our main aim is to determine the horizontal deflection at B. External work done is equated with internal work done. External work done is determined by half P delta and equated that with internal work done. The expression for horizontal displacement at the roller end can be determined. Till now, problems solved by strain energy methods were discussed. We shall see the limitations of strain energy method. Deflection can be found only under following two conditions. Structure has to be subjected to a single concentrated load, and deflection can be determined only at the loaded point and also only in the direction of the load. These two limitations limits the usage of this method to all types of frames and beams. If there are n number of loads, this method cannot be used. If deflection has to be determined at some other point apart from the point where load exists, then this method cannot be used. We shall see how deflection and rotation for those type of problem in our next videos. Here I will stop with this strain energy method. In my next video, I shall discuss about solving problems using virtual work method. Thank you.